Thanks, Bulent, and yeah, thanks a lot for this invitation. I'm glad to get to share some work of some students and hear a couple of very nice talks. So you may find this. So this was a report on an REU. So it's inherently meant to be a pretty accessible project because we wanted to create a project some students could work on. So um, there's a long list of participants, and that's because it's a research experience for undergrads. So Dan Irvine is these days he works in mathematical biology, so an applied mathematician here at Georgia Tech, a colleague of mine, and maybe a year and a half ago gave a talk on persistent homology and its uses in like mathematical biology and applied settings. And so I started talking to Dan about a bit of Legendrian contact homology because I had done REUs in the past on Legendrian contact homology. It's very amenable to student participation, and so we decided to uh, try to merge the topics in some way. So Dan is a fellow postdoc at Georgia Tech. Shen is a graduate student here at Georgia Tech who contributed a lot, and then Maya Basu, Ethan Clayton, and Frederick Mooers are currently undergraduates. But if you see some grad school applications coming across your desk soon from these three, look out for them. Okay, so just a quick idea of what I want to do is just rapidly remind everyone what Legendrian contact homology is, because I'm guessing many of us are familiar, but it's created by, in the same way that most Floer theories are, but it does have some subtle differences. And then what makes it sort of amenable to undergraduate work is that it has a combinatorial description due to Chekanov. Then I'll sort of pivot and explain why, if you want to talk about Legendrian embeddings instead of Legendrian isotopy classes, then maybe LCH is not good enough. I mean, it's perfectly good, but it's not going to be able to distinguish embedded Legendrians, which are isotopic to one another. And then I'll give a very quick description of persistent homology. This will probably be disappointing to those of you who know persistent homology because you surely know it better than I do. And then once we've given these three bits of background, the definition of persistent Legendrian contact homology is going to be more or less immediate at that point. And then the main result of the REU is the continuity of persistent Legendrian contact homology. It'll give us a continuous map from Legendrian embeddings to persistence modules. At the end, there's like one slide on Legendrian isotopies. I would be happy to run out of time before getting to that. So we'll see what happens there. All right. So what is Legendrian contact homology? Well, as I said, it's an invariant of Legendrian isotopy classes. So that's an important distinction to make. So given an isotopy class of Legendrian knots in the standard contact space on standard contact R3, you can choose a generic representative. In particular, you choose a representative whose Lagrangian projection has only these transverse double points as its singularities. There are no cusps or triple points that appear. And then the Chekanov-Eliashberg DGA, from which Legendrian contact homology is computed, has all of its data recorded in this Lagrangian projection, and you can define it, like I said, combinatorially without having to teach students anything about J-holomorphic curves or what a symplectic structure even is. So the generators of this algebra will be the intersection points of your Lagrangian projection. These correspond to Rabe chords of the Legendrian knot up in R3. And I said transverse intersection, but that's just built into the genericity of lambda. I don't want to describe the grading, but you can do this completely combinatorially from the diagram. And what it's measuring is the rotation of your contact planes along your Legendrian lambda. And then the differential is just some count of polygons in the Lagrangian projection. So in this example that's embedded in the picture here, or in the slide here, just one example of a differential is given. This is the differential of A1. This has four terms. There's a single, a one, there's just a unit because there's a polygon from A1 to nothing. You see A3 appearing because of, let's see if I draw it correctly, this polygon, which goes from A1 to A3. You get an A5 from another red polygon, and then the purple polygon will give us either A5, A4, A3, or A3, A4, A5, depending on commutativity. And then by definition, the Legendrian contact homology is the homology of this Chekanov-Eliashberg DGA. Okay, so that was a very rapid introduction / reminder. I mentioned that it's defined, like it's motivated in much the same way as any other FLIR theory, but there are some problems with like basically the Arzela-Ascoli step, the compactness when you're trying to get d squared equals 0. You have to compactify your space of curves in a weird way. Okay, so some of those comments are made here, that there is some rave action in the background. But one thing to notice is the Chekanov-Eliashberg DGA never has finite rank, because all of these generators, they're generators of an algebra. Like we only have 5 generators in this picture, but they're not vector space generators. So it's never finite rank. And so the graded rank of the Legendrian contact homology could also be infinite, and often is. So actually trying to extract computable information from Legendrian contact homology is often very intractable. One way to fix this, and this is also due to Chekanov, is via linearization. So if your DGA admits an augmentation, then you can define this graded vector space, which is the linearized Legendrian contact homology with respect to that augmentation epsilon. And so the trefoil that appeared on the previous slide, you can go through and compute the full Chekanov-Eliashberg DGA, and then that admits 5 different augmentations, and each of those augmentations gives the same linearized Legendrian contact homology. So this is just to explain the notation when we have a superscript epsilon. But here we can at least get finite rank homologies and actually compare some knots. So that was a rapid fire introduction to LCH and its linearized version. But what we want to think about in this RU project is when you do a Legendrian isotopy, by construction, you're not supposed to change the Legendrian contact homology. So here's a Reidemeister move in the Lagrangian projection, which actually can be realized. But this will certainly change the Chekanov-Eliashberg DGA. So if you want to distinguish between isotopic Legendrian embeddings, LCH can't do it, but perhaps the Chekanov-Eliashberg DGA can. In this case, we see that we've added 2 generators to our DGA. If you take the homology, you're not going to see those generators that you've added, but maybe at the chain level, there's some information you can extract which will distinguish the embeddings. And the analogy that is more suited to this crowd, but which I would struggle to comment on, is something like if you have distinct Hamiltonians on a symplectic manifold, then like the FLIR chain complexes are going to differ, but the homology is not, if I understand things correctly. And so this is some filtered chain complex, and we want to use that filtration to distinguish between that we're using as our inputs to build the chain complex. So the point of persistent Legendrian contact homology is going to be extracting some information at the chain level, which will let us distinguish Legendrian embeddings. Okay, so as commented on, there is an action. So the Chekanov-Eliashberg DGA is a filtered DGA, even though we don't normally think of it as such when talking about isotopies. And it's filtered by this very natural action functional where you integrate your contact form along paths whose endpoints are on your Legendrian. And the critical points of this action functional are the RABE chords, which then correspond to intersection points in the diagram. So this is exactly the FLIR theory that you might have wanted to write down. You just, like I said, run into problems with d squared equals 0, so your differential is a little weird. But once you have all these terms defined, making a definition of persistent Legendrian contact homology or persistent linearized Legendrian contact homology is almost automatic, because I still need to tell you what the persistent homology of a filtered chain complex is. But because the Chekanov-Eliashberg DGA is filtered by action, you can just define, take the persistent homology of that filtered chain complex or of that filtered DGA, and you get the persistent Legendrian contact homology and the persistent linearized Legendrian contact homology. That's a good point to pause before I say what persistent homology is. Okay, so to make these definitions meaningful and more meaningful than just a bunch of symbols, we can very, very quickly say what persistent homology is. Well, one thing we do require when we talk about filtered DGAs or filtered chain complexes is that our differential is filtration decreasing. So if you apply the differential and then compute the height of that image, you get something smaller than the original height. The reason we do this is so that now you can talk about your chain complex or your DGA having these sublevel complexes, sublevel subcomplexes, I guess, meaning I just want all of the elements up to height t, and then I can restrict my differential to that subcomplex, and it will map to the subcomplex. It is important here that I'm saying it's a chain complex. It's no longer a DGA because you could have two elements of height less than t whose product is not of height less than t. So we lose the algebra structure when we do this, at least the way I'm writing it down right now. So each of these complexes, or sorry, not each of them, but in between complexes, we have transfer maps. So here, this is just inclusion of the chain complex, where I'm saying if S is smaller than T, then you can include the chain complex into the larger one. And then I'm writing down these properties that are sort of obvious for those inclusion maps. But the point is, for each of these vector spaces, it's really the point is that we get a functor from the poset of real numbers to vector spaces so that we want linear maps which behave functorially. And then the persistent homology of your filtered DGA is this collection of spaces, this collection of homologies of your subcomplexes, your height T complexes, along with those induced transfer maps. So the persistent homology consists of both the vector spaces and or modules and the transfer maps that are induced by the inclusions. So this data taken all together gives you, oh, whoops, I forgot there's an example. I'll back up to it in just a moment. This data altogether gives you a persistence module because you have a functor from the poset category of real numbers to vector spaces. For every real number, there's a vector space, and then between real numbers, you get these maps. So here's one way to depict a linear version where here I'm not considering a DGA, I'm considering just a vector space with 5 generators. And as you see here, we have 2 generators in degree 1 and 3 in degree 0. So this is a chain level picture. This is the chain complex that we begin with, 3 things in degree 0, 2 in degree 1. But the filtration is such that we don't see the degree 0 generators until we get to height 1. And we don't see the degree 1 generators until we get to height 4. And thus, when you take homology, anything below height 1, you just see nothing because there were no generators yet. Between heights 1 and 4, you see a rank 3 homology in degree 0 and no homology in rank 1. And then at rank 4 and above, you kill off one of your generators in degree 0 and you gain a single generator in degree 1. Okay. So if we have persistence modules, so this is 2 separate functors, we want to be able to talk about essentially what we're going to describe is a natural transformation between those functors, if you want to speak in categorical terms. But we want to really define a notion of distance between 2 persistence modules. So we want to say if you take a filtration and you wiggle it just a little bit, then you don't really affect the persistent homology that comes out of this. So if you have these 2 persistence modules, a persistence module homomorphism of this should say like persistent degree delta. Degree is a little bit overloaded here. Is this collection of maps, which is going to take us from the height t vector space in the u persistence module to the height t plus delta in the v persistence module, so that this diagram commutes. So you have a transfer map from US to UT, and you have a transfer map from VS plus delta to VT plus delta, and we just want to say this sort of whatever this map is, maybe it's an inclusion, maybe it's a zero if that works, that makes this diagram commute. And then a 2 delta interleaving of the 2 persistence modules is one where we can write down a pair of morphisms. So we have a persistence module homomorphism of degree delta in each direction. So from U to V, as well as from V to U, so that the compositions just look like the identity morphism on each side up to this 2 delta wiggling. I think this is really hard to digest when at least it was for me, the first time you see it in just like a purely abstract categorical way. So there's another example of just a linear version of this where you see a barcode. And really what we're trying to capture here is that a 2 delta interleaving allows you to wiggle the endpoints of your barcode by like delta. So in this case, if this is a picture of U dot, and this is a picture of V dot, well, you can see that we have the same collection of bars in each of the 2 persistent modules. We've just moved the endpoints a bit. So here the endpoint was at 1/2, and then we've pushed it up to 3/4. So you could define a map, which is, I guess, the 0 map here at this height, and then becomes just the identity map once you get a little higher, or inclusion map or something. And you could do a similar game with the finite bar, where you say, well, my endpoint on the right is now smaller, so it has to be the 0 map because I'm coming from 0. But then after that, we'll have the identity. And so this wiggling was of like 1/4. So we would say that these are, oh no, I guess it's 2 times 1/4 interleaved. Because you have to do some amount of interleaving there. And this allows us to write down the interleaving distance between persistence modules. It's just the infimum of all of the deltas over which you can do this. So the distance between these 2 persistence modules would be 1/4. But you could have distinct persistence modules whose interleaving distance is 0. And that's why this is a pseudometric and not a true metric. So the space of persistence modules, we've not made it a metric space, but we've at least topologized it with this pseudometric. And we would expect then that if we start with some Legendrian embedding in R3 and we make some very small Legendrian isotopy, say one that does not introduce any new generators, we would expect this to modify the filtration by only a small amount, and therefore modify the persistence module by only a small amount. If we perform a Reidemeister move of some sort, so if we perform some sort of Legendrian isotopy which does introduce or delete generators, then you can also you can actually affect the number of bars that you see here, but we expect these introduced bars to be very, very short if you've done a very, very small isotopy. And so the persistence modules would still be nearby. So in this example, the number of bars on each side was the same. That doesn't have to be true for the interleaving distance to be small. Okay, so I guess a lot of what I just said, it appears again here, which is just, we can now, for one thing, because we have this filtration, we can visualize the persistent homology, or at least the persistent linearized homology with this barcode. And we want to ask, if we make some very small Legendrian isotopy on the left, so you use like a C infinity topology on the space of embedded Legendrians, will this map persistent Legendrian contact homology be continuous with respect to interleaving distance? Will we only introduce very short bars or wiggling of the endpoint? And I'm running out of time, but I'll just point out that there is a distinction between those isotopies which represent planar isotopies in the Lagrangian projection. So we do not change the number of generators of the Chekanov-Eliashberg DGA. And then those isotopies which do change either the number of generators or affect, if you do these triple point moves, you don't change the number of generators, but you do sort of create these non-trivial DGA maps between the before and after pictures. So the filtration, sorry, the Legendrian isotopies, which induce planar isotopies in the Lagrangian projection, those almost trivially induce very small interleaving distance moves on your barcode level. The thing that you really actually have to go check is the Reidemeister move portion of this. And there's the technical statement of our student's theorem, but the short version is that when you do these Legendrian Reidemeister moves, if you do them with heights that are very close to each other, so you have not changed your filtration very much in the course of this embedding, then you will indeed induce 2 delta interleavings when you have isotopies by some delta. And so the upshot, the corollary is that persistent linearized Legendrian contact homology is continuous with respect to interleaving distance, which is a nice result to have and perhaps could be used to make statements about the embeddings. So I succeeded in getting to skip the statements about isotopy classes and can thank you for your time.
Thank you, Austin. Let's thank our speaker. Thanks. Very good. Any quick questions for Austin before we start?
Well, maybe I have a question. So
sure.
There was earlier work about persistence in Legendrian context homology. So it started from Dimitroglou, Rizal, and Sullivan. I think actually they published a paper which more or less is called Chekanov-Eliashberg algebra and persistence. So we with Misha and have had a paper about persistence in LCH. So there was some study. And did you try, so I have actually 2 questions. My first question is, did you try to compare your work with earlier papers?
Yes, and I apologize. I certainly should have suggested this paper. I will confess I haven't looked at that paper since last summer, and so I don't remember the main result. But there is a discussion of that paper in the preprint that grew out of this project. Although I should say, I think maybe our project was less ambitious than theirs. So I certainly want to be as deferential as possible when it comes to assigning credit there.
Yeah, but I mean, it's, so let's forget about credit. Yeah, so it's, I mean, it's not that important. That's, the issue is, I mean, you're kind of advancing knowledge. So the question isn't where are you advancing it? I mean,
so I don't think that they.
And here
I will say I don't think they have this result, but I don't recall what result they do have.
I think that, for instance, certainly Dimitroglou, Rizal, and Sullivan, in some formulation, I don't remember all the assumptions, right? But moral is the following: that there is Shulugin-Hofer distance on Legendrian submanifolds, which is kind of much more robust, by the way, than C infinity topology, right? So it's like Hofer's metric and then smooth topology on symplectomorphism. So in principle, I mean, we can make quite a large deformation, right? And I think that this kind of LCH persistence model, in some sense, is continuous when you have interleaving distance on modules and Shulugin-Hofer distance on Legendrians. But again, I mean, I don't know it from the top of my head. But you certainly have to check this. This is the comment.
Yes, absolutely, and I appreciate you bringing that up. And like I said, in the paper, there is a citation of that work of Dimitroglou, Rizal, and Sullivan, but I just at the moment also don't recall what their exact statements are or what their hypotheses are.
Okay, thank you.
Any other quick questions? I'm about to stop recording. Very good. Okay, let's thank Austin and the other 2 speakers for wonderful talks.